Here is today's challenge. Inside this square are four identical quarter circles, one tucked into each corner, and perfectly nested between them is this tiny circle. Without measuring anything, can you find the exact radius of that middle circle? Pause the video if you would like to try it yourself. At first glance, it might look like you will need some advanced geometry. But as you will see, the entire problem comes down to one beautifully simple observation. Let's start by labeling what we actually know. Say the square has side length s. Each quarter circle reaches exactly to the midpoint of the sides, so its radius is simply s over 2. The only thing we don't know is the radius of the small circle in the middle. Let's call it r. So the question becomes, how do we relate these two radii? Now, your first instinct might be to chase the tangent points directly. Here's where the small circle touches each of the four arcs. You could try drawing lines to each of these points, hunting for similar triangles, setting up angle relationships. But very quickly, this turns into a tangle of unknowns with no obvious way forward. This gets messy fast. Fortunately, none of this is actually necessary. This diagram looks like it needs a complicated theorem to solve. But usually the hard part is in the math. It's noticing the right line to draw. Let's draw it. Let's mark 2 points. One corner of the square and the other center of the square. Right here. Now connect them with a single straight line. This line is the entire key to the problem. Here's why. The center of the small circle sits exactly at the center of the square. And each quarter circle is centered at a corner. So the first part of this line, from the corner to where it crosses the arc, is just the quarter circle's radius s over 2. And the second part, from that arc all the way into the center, is exactly r, the radius we are trying to find. That's because when two circles are tangent to each other, the distance between their centers always equals the sum of their radii. No exceptions, no extra assumptions. It just falls out of what tangent means. So the full length of this line from corner to center is s over 2 plus r. Now all we need is a second way to measure that exact same distance. Let's go back to just the square for a moment. Draw its full diagonal, corner to opposite corner. By the Pythagorean theorem, the diagonal has length s times the square root of 2. Now here is the useful part. The center of the square sits exactly halfway along that diagonal. So the distance from any corner to the center is just half of it. That gives us s root 2 over 2, which simplifies to s over root 2, a cleaner way to write the exact same value. So now we have two different expressions for the exact same corner to center distance. All that is left is to set them equal to each other. S over root 2 equals s over 2 plus r. Rearranging to solve for r, we subtract s over 2 from both sides. Factoring out an s, we can rewrite this as s times the quantity root 2 over 2 minus 1 half, which simplifies down to this. R equals root 2 minus 1 all over 2 times s. That's the exact radius of the tiny circle. No approximations, no measurements, just geometry. Now if the problem instead asks for the area of the small circle, we already have everything we need. Just plug our radius into the standard area formula, A equals pi r squared. Substituting in what we found for r and simplifying, we land on this. Pi times the quantity 3 minus 2 root 2 over 4 times s squared. Surprisingly clean, closed form answer for a shape that looked far too irregular to pin down at the start. This problem is why I love geometry. The solution did not need a complicated theorem, just spotting that one line, from corner to center, was the distance between two tangent circles. Everything else followed. If you enjoyed this, subscribe for more puzzles where the hard part isn't calculating, it's seeing the idea. Spotted the trick before I revealed it? Let me know in the comments. I'll see you in the next one.